Good morning, and I'm very happy to be here. I spent 10 years of my life in the building next door as an undergraduate and graduate student here. And in that wonderful period, I had many memorable moments, including the courses that I took from Yakir. One such memory is particularly relevant for this conference. I was, I believe, a third-year undergraduate when I first heard about the AB effect, and I was standing in the lobby of the physics building explaining the effect to a fellow classmate. And after some time, we realized that Yakir, don't know if you remember that, you were standing a small distance from us, probably overhearing me, explaining your effect. And you were looking at me and smiling, which I took as approving of my explanation. And I hope that after this talk, you will still approve of my understanding of the AB effect. So actually, this is a double feature Yakir-Aharonov because the work is based on two seminal effects by Yakir, the AB effect and the weak value protocol. My collaborators are Alessandro Romito of the University of Karlsruhe, and actually he will add some details in the next session. Jaroslav Blanter from Delft, the late Vadim Shpitalnik, and my student Oded Zilberberg. And as I said, this talk is based on three seminal works Yakir has co-authored: the AB paper, the paper on two-vector formulation of quantum mechanics, and then the paper by Aharonov, David Albert, and Lev Weidman on weak value protocol. So the outline of this talk will be the following. For those of you who knew but forgot what weak value is, I will give an ultra-fast introduction. Apologize for those who know. Then I will talk briefly about two examples of implementing this protocol to a real-life quantum solid-state problems. Now, 2 years after this, more than 2 years after this project has started, we find ourselves now at the stage where we understand the tools, we know how to apply them to real solid-state problems, and presently we are working on really implementing them to problems where we think we go beyond the curiosity of the protocol. We hope we'll really gain insight of that is not available by other methods. But that further step presently under work will be reported hopefully in a future conference. So I start with the ultra-fast introduction, and just to emphasize some of the benefits of a weak value protocol. It allows us to measure correlations in quantum mechanics, or to access correlations in quantum mechanics which are otherwise not easily accessible. It allows us, in principle, to measure simultaneously two non-commuting variables related to two non-commuting operators. It allows us to access virtual states, for example, a particle under the tunnel barrier. It has some potential applications in metrology, and there is another possible application which I will not discuss here. So in a nutshell, a weak value protocol consists of 3 steps. In the first step, we prepare the system in an initial state can be a pure state. It can be a thermodynamic mixture. Then, at a later time, we perform a weak measurement of some observable, which is represented by an operator B. And by weak measurement, I mean that we very weakly disturb the state of the system, or almost do not disturb the state of the system. I will come to that a bit later. So we write down the result of our experiment, and at the third step, we perform strong measurement, projective measurement, of another operator, A, such that A and B do not commute. And now the rule of the game is that if the outcome of the last step is such that we hit some particular pre-chosen, pre-selected eigenvalue of A, then we do keep the outcome of the weak measurement. Otherwise, we cross it out from our notebook, and we start this all over again, and we collect data, and eventually we average over this data. So in a more precise way, slightly more precise way, what we do is the following. We prepare the system in the state psi initial, and this is the mean value of the operator B. Now, this will be the only mathematics in this talk. So now we insert a complete basis here in the middle. And for this complete basis, we use the eigenstates psi final n of the operator A. This is the operator used in the post-selection step, in the last step of our procedure. Now we multiply and divide by the scalar product of the initial state and the final, one of the final states, psi final n, and we sum over n. So, so far we haven't done anything, but now we can interpret this expression in the following way. This is a sum over all final states of the conditional probability that we started with some initial state and we ended up with some final state, psi final n, and each of these conditional probabilities is multiplied by this factor. So this is this factor. Now we come to the weak value protocol. As I told you, we keep only those results that ended up with one particular psi final. Let's call it psi final naught. This means, first of all, that for that particular set of measurements, we need to cross out the summation because we have only one result that we keep. And secondly, we know that for that particular result for our data set, which we keep, we know for sure that that resulted in psi final naught, so we can cross out this conditional probability altogether, and what we obtain is this particular term, which we'll call the weak value of B. So the weak value of B is the value of B with the constraint that we started with psi initial, and we ended up in the post-selection part with psi final 0. Again, the expression we obtain is that we take this sandwich of B between the initial and that particular final and divide it by this initial over final. This was sort of mumbling words, but actually one can arrive at this expression by going microscopically to a Hamiltonian to describe a system, a detector, the interaction, and describing in a more precise way, this microscopic way, this procedure, we obtain this expression. Let's see how this works, and this is a canonical example of an application of a weak value protocol. We start with we have a beam of spin half particles which do not interact. We prepare each of these particles in a pure state, SZ up, SZ equals plus a half. At a later stage, we weakly measure the spin projection in the 45 degrees in the XZ plane. and then we write down the result. And then at a later step, we perform a post-selection. We measure the spin projection in the x direction. If, for example, the spin projection is spin up, Sx equals plus a half, we do keep this result. If it's Sx equals minus a half, we cross out the result, and substituting it now in our in this expression, we obtain the following expression. Psi initial is Sz equals plus a half. Psi final for that particular example is Sx equals plus a half, and the operator B is the spin projection in the xz plane 45 degrees. After 1 minute of calculation, we realize that the result is square root of 2 divided by 2, which reveals one of the non-intuitive aspects of a weak value. If we strongly measure the spin projection in the 45 degrees in the xz plane, then sure enough, each measurement will give us either plus a half or minus a half, and average over these results will give us some value on the interval between minus a half and plus a half. But this procedure with the post-selection, a conditional probability of post-selection, give us something, a value, which is beyond this range of eigenvalues. So this is a curiosity. The question is what this is good for, and this is what we are headed. So that was my ultra-fast introduction, and let me now go to two examples based on solid-state physics, and let me start with a spin-based qubit, the double dot qubit. So before that, let me recall that a strong or projective measurement requires two elements: the observer or the detector and the system. And once the observer measures the system freezes or collapses and then freezes in an eigen state. This is the von Neumann description of a measurement. By contrast, when we have the weak measurement, the observer observes the system with nearly not disturbing it. Of course, we pay a price, and the price is that we have a very blurred view of the system, or we obtain very partial information about the system. So let me be a bit more quantitative and give you an example from real-life quantum solid-state physics. So here we have a double dot. These are two quantum dots which are tunnel coupled. And as a first step, we are going to put one electron on this structure. This is our detector, which in the jargon is called quantum point contact. This is a wire of nanoscale dimensions, at least as far as the width is concerned, in which current flows. Now, there is a bottleneck, a constriction here. And the bottleneck, the shape and the strength of this bottleneck will depend on the electrostatic potential induced by the electrons. Whether this electron resides on the right or on the left will affect the strength of this bottleneck. So now the next step is that I'm sorry that the colors didn't come up visible. I hope you can still see it. So what we want to measure is the total charge transferred through this quantum point contact over time delta t. And this total charge Q is just the integral of the current over this time delta t. Now, the probability distribution of this current is noisy, so we are talking about probability distribution, will depend on whether the electron is on the right, in which case we have this sharp distribution, or on the left, in which case we have this sharp distribution. But if we detect a value of Q, which is here, we can say with confidence that the electron was on the left. Now, we make this measurement weak. We can make this measurement weak by either reducing the coupling to the system, the coupling of the detector to the system, or by reducing the current that flows in the system. And now we have two distributions that overlap. So the distribution will be this one if the electron is on the right, or this one if the electron is on the left. But if this means that if we measure a value of Q, which is here, we can only ascertain probabilistically that there is more chance that the electron was on the left than on the right, but we cannot say it with confidence. This is the blurred view of the system. This is the lack of information. I mean, we do have some information, but the information is not complete. Now, in principle, one can use this notion of weak measurement as a part of the weak value protocol. For example, this electron may perform Rabi oscillations between right and left, and we can weakly measure the location of that without perturbing the Rabi oscillations, and then perform post-selection and so on. The main problem here in such a system is that we will have very short coherence time. The system decoheres after a time which is of the order of 10 picoseconds. And 10 picoseconds for such a protocol is too short to implement an experiment. So we need something that has a longer coherence times. And our suggestion was to implement a device, a system that was designed and measured and characterized by the Harvard group, by Charlie Marcus and Amir Yacobi. So here we have two dots, which are defined by gates. This is dot number 1, this is dot number 2, and this is our quantum point contact to which current flows. Now, the two lowest, and now what we are going to do, we are going to put not one electron, but two electrons on this device, and we are going to make use of the spin degree of freedom of this system. So the two lowest states of the system with two electrons are described here. This is a singlet. The singlet is a hybrid between singlet 0,2, 0 electron on the left, 2 electrons on the right, and singlet 1,1, 1 electron on the left, 1 electron on the right. We can travel along this curve by changing epsilon. Epsilon is the difference between the electrostatic bias on the left dot and on the right dot. The next state, this straight line, is a triplet 1,1. 1 electron is on the left, 1 electron is on the right. Now, we can control and play with the system by playing with two handles. One handle is playing with the difference in the electrostatic potential of the two dots. The other is by a clever, effective use of a nuclear magnetic field. I don't have time to discuss this. So the upshot of this is that we have included the spin degrees of freedom, which would mean that our decoherence times are large. Decoherence times for charge degrees of freedom are very short. For spin degrees of freedom are large. So we are talking not about 10 picoseconds, but about 10 nano up to 1 microsecond, which are very long time scales. Experiments can be performed within this time scale. Secondly, we introduced the spin degrees of freedom. What we can actually measure with our quantum point contact are charge states. The quantum point contact is sensitive to charge, whether it's 0,2 or 1,1. What we actually control or play with are with the two states, triplet and singlet, which form some pseudo spin states. So this is a Bloch sphere of a pseudo spin. The two poles relate to a singlet and triplet, and by a clever manipulation of the electrostatic charges and the nuclear spin, we can rotate the system and play with it on the Bloch sphere. and as well as perform weak measurement and then a strong measurement. I skip the details, but this is the outcome. So we have in the protocol we propose 2 tuning times of epsilon, which I denote as delta and theta, and the quantity we measure is the total spin, not the spin projection, the total spin. The total spin. So look here at this scheme. The total spin of 2 electrons in strong measurement should be any number between 0 and 1. Over these colored regions in our parameter diagram, we have reddish and bluish parts in which, respectively, the weak value of the total spin can be larger than 1, or we can even have a total spin whose value is smaller than 0. So this is, again, the peculiarity of a weak value. And finally, I want to say a few words about Mach-Zehnder Aharonov-Bohm interferometry. This is an electronic Mach-Zehnder interferometer, which has been discussed again and again and again yesterday. Electrons or quasi-particles can move along chiral edges of a quantum Hall system. So we emit particles, electrons or quasi-particles from this source. And after following these trajectories, possibly tunneling to the other edge, following these arrows, they can be eventually absorbed either in detector D1 or the detector D2. So the weak value protocol will consist of this system and a detector which by itself is another Mach-Zehnder interferometer. And now we have a weak measurement of the current flowing through here and a strong measurement or post-selection of the current absorbed in D2. So we measure weakly or weakly couple this detector to this arm. We measure the current to this arm very weakly, and we include the result of this measurement only provided that this current pulse will be absorbed in this detector and not in the other detector D1. Again, I don't have time to go through the mathematics here. That will be done by Alessandro in the next session. But I want to emphasize three ingredients that we learn from this protocol. The first is that the weak value here, in this case, is complex. And by using as a detector another interferometer, which by itself is sensitive to phases, we can retrieve both the real and imaginary part of the weak value, so we have a full tomography of the weak value. Secondly, we have specifically introduced the temperature and the non-pure state, mixed state, and we have seen how the features of weak value are reduced. For example, the Aharonov-Bohm modulations of the weak value are reduced, are blurred a little bit. The visibility of the Aharonov-Bohm oscillations is reduced. Most importantly, in this formalism, we have used a many-body formalism. I think this is the first time that this is used in this context. What we, the main message here is that as compared with a single particle analysis, when we discuss a many-body analysis, the weak value effects are somewhat smeared. They are smeared by two factors. One factor is like. I don't want to call it a Johnson or Nyquist noise, but it's like a Johnson noise-like term, something that appears like a thermal noise. The other term is something that is proportional to the current, is the analog of a short noise. So there are two factors that attempt to reduce this weak value. So in summary, what I reviewed the weak value protocol, and there are 3 steps. Secondly, I showed you this outcome of trying to measure, to define the weak value of the total spin of 2 electrons on a qubit. And one can obtain a weak value with S larger than 1, S smaller than 0. And finally, I spoke about full tomography and many-body effects within a weak value of a double Mach-Zehnder interferometer. Now, there is, some of my colleagues are critical towards this line of research. And the main critique is that, okay, fine, this is a nice protocol. There are some peculiarities, but the peculiarities are embedded in the definition of the protocol. So after the first shock that one obtains non-expected values, one goes to the other extreme, saying, okay, this is trivial because this is part of the embedded protocol. So actually, I hinted to that in the beginning. What I described so far is the design and the training, practicing the tools. Presently, we are working on 2 problems, and I believe that in these 2 problems, one can really obtain insights into with the help of weak values, but I'm not ready to talk about it here, so thank you very much.
We have time for 1 or 2 questions.
The fundamental theory of weak resonance, the newest form of it, the strange events, strange measurements outside the eigenvalue spectrum and so on, are also rare. Huh? So how are the statistics? If you want a very strange result, you generally need to the post-selection must be rare.
Sure. Okay.
So there must be some
trade-off.
Some fight.
Absolutely. And actually, there was a hint here in the phase diagram that I showed here. Because if you note, the red or the blue colors hint at unexpected values. So you see that there are some U's in this color scheme. So the more, I mean, if you are willing to take a value which is strange, but just below 0, you will have a rather large finite fraction of this phase diagram that gives you this value. But if you want to be something below -2 or below -10, then there will be increasingly. Okay, so that depends on the problem. For our problems, we have a mathematical expression of the trade-off. But I don't believe that this is, at least I don't know of any universal statement about how far you need to go from a.
Have you made estimates?
For this, yeah. For what I'm saying is, for these 2 examples that we worked out, we actually have mathematical expressions. We worked out the mathematical expressions and so on, and all is written.
Just one. Yes.
You said that in the Mach-Zehnder thought experiment you could see perhaps the effect of collective behavior. And you mentioned shot noise, but I don't see how shot noise reflects collective behavior.
Okay, so what I was careful in formulating it. What we have done was to discuss this weak value in the context of many-body physics. So I don't have one particle. I have one particle on top of a Fermi sea. Or, I mean, since we are dealing with the edges, we are talking about a compressible liquid. We didn't include, so we included many body formalism, and within this you have short noise and you have Johnson noise-like. We did not include interactions, really. I mean, the only interaction is between the detector and the system. We did not include interaction in the gas of particles. This will be the next step. But at least already on the step of many body non-interactive particles, we already see additional terms.
I think we really have to stop now because, let's say, we are really but pressed on time. Please let me want to make
Yes, say.